temperature sensors, let's go back and review what type of temperature sensors did we talk about? I'm waiting. What type of temperature sensors did we talk about? Are we just reviewing the last lecture? Yeah, we started off with a thermistor, right? And what does a thermistor do? Based on temperature, right? It's non-linear. What do we mean? That means its resistance does not vary in a straight line. So what we do to compensate for that, we either do it electronically or we do it with just using a small span, right, of the actual sensor. We have two types. We have what? NTCs, and which is the one we looked at, and we have PTCs. And what's an NTC and a PTC? Coefficient, right? So an NTC, its resistance goes down with temperature. And PTC, its resistance would go up. And the only one that we've got around here is an NTC, the NTC. And what was the other one, Jose, you said? No, a thermostat is a thermocouple. And what does the thermocouple do? It wouldn't be a regulator, because a regulator tries to maintain something that's constant, right? You understand? This guy, if it was constant, it wouldn't be measuring temperature, right? So what does a thermocouple do for us? How does it measure temperature? All these are temperature sensors. What does it vary? What does it produce? That's how they make them, but how does it measure temperature? So we have two dissimilar metals that we bond together, right? And Alex brought his in so we could actually look at the bond of the thermocouple. But what does it do? First of all, are they linear or non-linear? These guys are linear, right? You understand that. And what do? So a thermistor changes its resistance. So if I need a voltage out of a thermistor, I'm going to have to use it either in a Wheatstone bridge, right? You understand? With Wheatstone bridge allows me to set a zero reference, or I'm going to have to use it in series with a resistor, right? Everybody understand, with a fixed resistor. But there the reference doesn't really mean anything. So what does a thermocouple do? So a thermocouple produces a EMF, electromotive force, that is proportional to temperature. So it actually produces a voltage, which can produce a very small current, right? You understand that? So these guys actually produce a voltage that's proportional to temperature. And we have different metals that they use that would actually give you the range. It says there in Explorer subboarding. something that's got a little bit of resistance. They choose the size, they choose the length, and then after that, the temperature would be the resistance would be proportional to temperature. So what is it? What does and when you said insulators, does the insulator affect the affect resistance? Yes, but because of what? So what I wore a jacket in today. Why did I wear a jacket in today? That's an insulator. Keep me warm. So what did it do? It varied my temperature, right? But it varied the temperature, right? You understand that? So that's the insulator affects it that way, because the metal cannot dissipate the heat that's being generated. Now, every conductor has an R. If you put I through an R, you get heat. If you put an insulator around it, then the wire cannot dissipate the heat as fast, and its resistance changes. So if you look up if we could, I can't get to my file server, but if you looked at how much a 14 gauge wire could handle in 25 degrees centigrade uninsulated copper wire, that sucker can handle 30 amps. NEC, National Electrical Code, rates a 14 gauge wire at 15 amps. Why do they rate it at 30 amps? Well, the 14 gauge is rated uninsulated 14 gauge wire at 25 degrees Celsius is rated at 30 amps. NEC rates a 14 gauge wire at 15 amps because it's insulated and it's designed to run through the house, right? You understand that? So they're saying NEC says I could run this thing up in Alaska, or I could run it out in New Mexico and it still be rated at 15 amps, right? You understand? So they're compensating for what the insulation and the temperature is operating. Yeah, a lot. And then you still have to dirate it if you run it so far. Mr. Sanders would know that. He's actually. Yeah, ceramic or glass, an insulator, right? We okay? Okay, what was the last one we talked about? There's the mister. Notice this guy is nonlinear, right? You understand? This is a chart for an NTC, a certain NTC. Basically, when you look at the data sheet, they give you temperatures and they give you ohms, and then you could develop a curve. You could develop the diagram if you needed to. But if you knew the chart and you knew the resistance and you were playing around with a computer could very easily run the math to give you a linear temperature, right? You understand? Or we could do it electronically. These guys are non-linear. What we do is we just compensate it for it by operating it over a narrow range. So this is what's used in your house. So your thermistor, your thermostat in your house, basically everyone I've ever seen, except for the old ones where they use a metallic strip, the newer ones, the digital ones, use thermistors. And how do we make them accurate? They're pretty accurate. We operate it over a lot. We operate it over a real narrow range. Everybody okay on, I call it centigrade. We don't call it centigrade anymore. It's officially been named to what? Celsius. Yeah, the name is officially been changed to Celsius. So what's the centigrade scale? What's 0 on the centigrade on the Celsius scale? 0, and what's boiling? And what altitude is that at? Sea level. Yeah, so all these scales are at sea level, right? You understand that? Okay. Then the Fahrenheit scale, what's freezing on the Fahrenheit scale? 32. What's boiling? 100. Then 212. What do we have? What do we have? Then we have what we call the Kelvin scale. What's Kelvin scale based on? Yeah, but zero is what we call absolute zero. That's been calculated. It's never been reached. It's big. Yeah. Huh? We'd be in trouble. Everything would be frozen. Everything. Huh? They would pretty. That would be probably not on Pluto, but in between the planets that might reach it. But as far as I know, it's never been reached. It's been calculated though, because they can measure the motion of molecular motion, and they drop it a certain amount of degrees, and they show how much it actually slows down. Right? You understand? And, it's cold, but we go inside something. Well, no, then you have heaters. So even the spacesuits that they go out in space are heated. They're actually heated. Right. It's temping. It's sensing it. No, it's sensing wherever your thermistor's at. Now here they have we don't have a thermostat. We have a sensor in every room in this building, yeah. And our sensor is where's it at? Right there. So that's it on the wall. That's it on the thing right there. Yeah, and they can technically control the temperature in any room. Really? I guess we could bring a can of freeze spray over here, but it runs on a computer. They actually set our temperature up on the hill, up in maintenance, up there on the top of the hill. Computer, yeah. This building, I know we have a sensor in every room. Yeah. And technically, what they do is they run the air conditioner and the heat all year long, and it's got a vein up there, and they tap into which one you get the most, which is pretty neat. And then we looked at electronic sensors. Oh, and then we have Kelvin. This is it uses the same station as the centigrade scale, but zero on the Kelvin scale is what we call what's calculated to be absolute zero. And then Rankin it uses the same station as the Fahrenheit scale, right? You remember that? It depends on the math formulas and what they do. A lot of times they'll use either Rankin or Kelvin. So we have one where we calculate the we don't we show you how to calculate the actual dynamic resistance of a p-n junction. And they use Kelvin in that. It turns out to be approximately 25 millivolts over emitter current. Okay. Yeah, we use 25 millivolts over. It's interesting to see all the math how these physicists come up with these numbers that we use as constants right now. So, yeah, and because we don't use because scientists don't usually use the Fahrenheit scale because it's so weird because freezing is 32 and boiling is 212. Yeah, and the rest of the world is using Celsius, and yeah, we're still on we call it the U.S. customary because we're I think there's only two or three nations now using in the world that uses the scales that we use. They made an attempt. Some of y'all are too young to remember it. They made an attempt one time to change us over So we had 2 mile markers all the way up the interstate. One of them was in kilometers and one of them was in miles per hour. And the cars came out, started coming out. They had 2 scales on it. They had one on kilometers and they had one, and the speeds were posted top and bottom on Fahrenheit. You see who won, I mean, on the miles per hour, and you see who won out over that, right? We're a very stubborn country, so yeah. When we was overseas, that would you'd be in a taxi and you'd look over there doing 90 kilometers and you'd go, "Ugh," but it wasn't that fast. And we won out. Of course, we won out over that battle. So we're still using. So okay, on the different temperature sensors that we went over, could there be some more? Sure. We just went over the basic ones. Of course, what we're going to use is we're going to use an RDT that operates off of 24 volts DC. So we're going to have a little power transformer, and then we'll use to have 2 relays, and y'all have to figure out the 2 relays, guys. And it's a 4-wire sensor, which means what? Need a power source, but it's a 4-wire sensor. So what does that mean, a 4-wire sensor? So we have 2-wire sensors that we played around with this semester, and a 2-wire sensor powers up through the load, right? You understand that? So that was our inductive sensor, and so here we had 2 wires, and then we had different variations, but right. And what was the colors? Yeah, and blue. And it powered up through the load, right? You understand that? Then we have a 3-wire sensor. Hmm. So what we're doing is we call this contact right here. What do we call this? What do we name that guy right there? We called it a single pole, single throw. So that's basically what we're simulating with these sensors. They're not actually relays in there. We're actually simulating them. And then we'll over here, and we'll have this that will go to the load. Now this is going to be what? This is going to be brown. This is going to be blue. But this right here is going to be what? That's going to be black, right? A 4-wire sensor, we're simulating one of these. This would be white. This would be black. And this will be our input. Actually, would go out to the brown, right? So a 3-wire sensor, all we got is a simulated normally open contact. A 4-wire sensor, we have a normally closed contact and we have a normally open contact. And the normally closed contact would be white. And we could come over here and take the white and connect it to another load. So these are our sensors. These are solid state sensors. So we got 2-wire sensors, right? You understand that? Solid state sensors. We're going to operate these are going to be high voltage sensors. They usually operate on like 120 volts. We could have a 120 volt sensor. So we can afford to lose. We can afford to lose some voltage across the sensor itself, right? You understand that? inducted sensor, when it was generating a trip, it still dropped around 4 volts because it needed it to operate, right? Understand? Get power to operate. But we still, that leaves us 116 volts that are low, which was well within the limit of that 100 volts that was rated 120 volts. Well, when I get down to 24 volts, which is the preferred voltage now used in industry, and why? Why is 24 volts? It's a lot safer. And why DC? Because the controller, the internal portion of the controller is an electronic, and it operates off DC. So when we had AC PLCs, they actually have a power supply inside of them, right? You understand? It's DC. We don't have to convert DC back into DC, right? You understand? So the preferred method in the industry is your program controllers are going to operate off 20 volts. Now these solid state sensors cannot afford to drop 4 volts, right? You understand? So that's why most of your solid state sensors that we operate in 24 volts will be 3 or 4 hour sensors. Now, what our sensor does is up here, these are relays. These are control relays. And they're single pole, double throw control relays, and we'll have to figure out which one. And then what we'll do is we'll come down here and we'll use a CR contact to do whatever we want to do. I'm just going to put a light bulb up there. But we might call it CR1 and CR2, right? And I don't know which is which. I don't know which relay they have connected to which output. So that's something you'll have to figure out when you trip it to see if the light comes on. If it comes on when it's supposed to go off, you'll just move it over to another terminal, right? Everybody okay? And our temperature sensor is an RTD, which is a what? Yeah, and what does that mean? The sensor actually varies its resistance with temperature, but it's electronic, so we got the threshold circuit inside there, and it's got a span we can set. And what is a span? I need to make sure I put that in. Basically, it's a range. It's a range, so we have the ability to set a low, and then we have the ability to set a what? High, and that would be a range. So it's like your two level. It's like your 2-level that you're doing on your lab, where you use 2-level sensors, where you run it till it get to a certain height, then you cut it off, and then you run it till it drops down, right? So what you're doing is you're setting a range within where that tank would hold its water. 2-level control. So we have 2 adjustment barrels on there that we turn to set the upper limit and the lower limit, where you want it to trip on and where you want it to trip off. Shouldn't hear it click. Well, you can, because this has got relays on it. You're right. We'll just have to figure out which one, how they got the relays hooked up. That's a relay in there, because it's got to turn on. What your thermostat usually has in it, it has an electronic circuit now, right? You understand? And it's got a span too, because if it didn't, it would be turning off and on all the time, right? You understand? So it gets up to a certain temperature, and then it turns off, and then it lets it do what? Some, right? Then it click back on, yeah. And what it's doing is picking up a relay. So that guy's. So what is thermostat? What voltage does thermostats in your house operate off? We'd be getting people killed all the time. 26, good. 26 volts AC. It operates off 26 volts AC. but your compressor and your fans operate off of 240 volts AC. So how can we take 26 volts AC and control 240 volts AC? Relay, good. So the relays have 24. The relays have 24 volt coils on them, but they control what? 240 volts on your motor. And that's what we're going to do here. So even though the tip switch is actually operating off of 24 volts DC, its outputs are going to pick up relays. And what can we put across those contacts? We can put 120 volts AC across those contacts. So guys, computers aren't doing away with relays. They do away with a lot of them, but they don't do away. No, I don't need to lose that piece of paper. Yeah, that shows me what I'm going to add back on. So, load or weight. So this is something that we measure quite often, right? Let me get the right. Let me delete this, by the way. Yeah, scales. That was one of the jobs I had when I got laid off from U.S. Steel. They worked off of levers. They were lever scales. Yeah, so they had levers. And of course, they came out with what we're going to talk about here in a minute. You don't see many lever scales anymore. Then we had some scales that operated off of what we call calibrated springs. You know, springs will compress and expand at a pretty precise force. So a lot of these scales still use those, like in grocery stores and stuff. That's over there in your vegetable place, produce section. Yeah, they still use calibrated springs to give you a good idea. But that when you go over to the checkout, those are not springs. Those are what we call load cells. They work off load cells. They just have them different size. They come in different. Yes and no. It's what we connect them to. A load cell is right. They come in different weight capacities. So you're exactly right. They had some scales out at U.S. Steel that were unbelievable. We worked on truck scales, which is a So what determines the resistance of a wire or metal? Sorry. That was something. What? Material. This guy don't work too good, guys. Size. Length. That was on the test too, wasn't it? Something like that on it. And they did And that was weird. Y'all had to drop like 3 questions. Y'all had to drop 3 questions. So material size, length, that's supposed to be an H, and temperature. So what we're going to do with what we call a strain gauge is we're going to use these 2 right here, and then we're going to compensate for temperature. Go ahead. Yes, it would, unless we compensated for it. And that's what we're fixing to talk about. How do we compensate? So I can, so basically, if I take a piece of metal and then I bond it so it cannot move to another piece of metal, and then I come up here and I apply weight on this, what it would do is it would cause this thing to squish. Y'all have all seen that, right? And you can take like a balloon and you can push on it. Well, what it would do is it would take this conductor and not only make it fatter, it would make it shorter. So that means the size goes up, the length goes down, so the resistance of the wire would go down. If we bond it to something that actually changes, right? You understand what I'm saying, yes or no? Okay. And it amazes me, and this is basically the way a load cell works. So what we do with a load cell, it uses what we call strain gauges. Strain gauges are nothing but wires. And we bond those wires to the side of something that basically changes its shape with weight. And if it changes its shape with weight, then this thing is either going to get longer and wider, or if it's going to get shorter and longer. That makes sense. So what we do is we just take a bunch of wire. Let me get out of this. So what we do with a strain gauge, so that's all there are, guys. It's just a loop of wire. And this is kind of opposite. So look at the way these things, so these are nothing but loops of wire. And in here, the force would be applied to this one. This is what we call the active gauge. And what happens when I push a force on this thing is going to compress, which is going to cause the wires to get fatter and the length to get shorter. So this guy right here with various resistance with length, right, you understand, in size. But the problem is that what? But also various weight with temperature. Hot or cold. So that means I've got a scale out there weighing these trucks, and it weighs different in the summertime than it does in the wintertime. That would be awful. So what we do is we put a compensating gauge that's perpendicular to the force. So this guy right here acts like an accordion. So it's not changing its length or size. All it's doing is spreading it apart and putting it together. And we run these things in unison with each other. This one right here, it varies its resistance with temperature. This guy varies its resistance with temperature and weight. This guy compensates for that. Well, how can we do that? Well, we put it in something called a Wheatstone bridge. So here, this guy's fixed. Then this guy is the what? This is the active gauge. It's varying its resistance with what? Weight and temperature. This guy varies its resistance with temperature. So that means if this goes up with temperature, this goes up exactly the same amount, and the ratio stays the same. You understand? If this one changes weight, the ratio is different, and it develops an output voltage that's proportional to the weight. So normally we always run these in pairs. They're mounted right beside each other. One of them's mounted this way, one of them's mounted that way. And they are inside, they are mounted together on whatever's warping with weight. So all we got to do is have something that changes its state with weight. We run these things in pairs. to use a Wheatstone bridge to balance it out, right? You understand, to balance out the variation in temperature, and then the accident, what we get out of accident would actually give us a voltage output that's proportional to it. And these things don't use much, like 10 millivolts per volt. So at least if you excite the 60 volts, you only get 150 millivolts out at its maximum. We can sense it, right? So these are some. So a load cell is a combination of whatever it uses to warp to change its shape with weight. And then it's got the Wheatstone bridge inside of it. You never see this. They got 4 wires. 2 of them you bring the excitation voltage on. 2 of them your voltage is proportional or extreme accurate. The only thing I do is figure out how to set it 0. And what we do there is we do it at the scale. You understand that? Actually, read out. So we calibrate these. We had a truck that carried, I think it was 50,000 pounds of weights, calibrated weights, and that's why we would calibrate the big truck scales. No, they don't because of this. Yeah, because this guy, if resistance go, and they're mounted right beside each other, so they're always at the same temperature. So what happens? What was you saying? So if this was 1K, and then this right here was 1K, of course that would be what? That would be whatever this excitation voltage is. So if this is this would be 10 volts, right? And then over here, this would be the difference. You know, this might be 3K and this might be 8K. It doesn't make any difference. So what I'd do is I would get a voltage out of it, right? But if this went up to 2K, then this right here would go up to 2K because of temperature, and it would still be balanced. It'd still be balanced, right? You understand that? So we would still have 5 volts right there. But if this guy went up, let's say if it went up to 3K because of weight, this guy right here would still be sitting at 2K, and now it would generate an output that's what? Proportional to the weight. But this is why we run these things in pairs if I want to get an accurate weight measurement. If I'm not interested in the exact weight, then we could run it by itself, and we can say, okay, and they put a lot of strain gauges even on buildings inside the big metal braces on the building, and they can tell exactly how much from a wind standpoint of view. They can tell how these big buildings actually move with wind. They actually move, yeah, and they can move quite a bit. It's unbelievable, you know, how much they can actually move. These big, tall skyscrapers, and you get all that wind pushing on one side. That's a lot of pressure. You know? They got one in Japan that's got a big old counterweight on it because it's so tall, and it actually shifts itself around to compensate for the wind, which is pretty good. And they can see that big old thing moving. Yeah. Oh, really? I mean, so we'd have something. The big truck scales. These were I can't remember the weight on. That's like 50,000 pound scales. They would fit. We had some 100,000 pound load cells that we had that measured rail. These were on our railroad that measured trains, and then you put them one on each corner, which would give you 400,000 pounds that you could measure on the scale because it would be balanced out between the three, four sides. What amazes me was the actual uh, piece of metal that warped with a big chunk of steel. And you think, well, how did a big chunk of steel actually warp? But it does. If you put enough weight on it, it will literally shrink and bulge out. And it causes the load cell, the active gauge, to shrink and bulge out, which basically increases the gauge and the size of the wire. So this would be a load cell. So a load cell it has the Wheatstone bridge built inside of it. It's got the two strain gauges mounted opposite of each other. One of them's for temperature compensation, one of them's to measure the weight, and then you have four wires running out to it. Two of them we call the excitation voltage. That would be actually powering up the Wheatstone bridge, and then the two of them would be your actual output of your scale. I mean, of your load cell. We call it a net weight or tare weight. So what you do is you have a button on your scale that says 0. You press that button, it zeroes out everything that's on there. So that's what we would do. So you have to zero out the scale. We bought a scale. They bought an electric scale. The problem we have with big truck scales is that it gets debris on it all the time. It was on what we call the line scales. And, those things comes to auto zero, which means if there's nothing on the scale and there's no motion on the scale, which means there's something on there, these guys constantly zero themselves out. And then when you pull something on there, you're not getting the weight of the weight bridge, you're getting the weight of the vehicle, right? You understand? And they would weigh twice. Y'all see the big trucks up here, the garbage thing weigh twice. So they come in, they weigh coming in, and then they do what? Weight going out, and they subtract the two. That's usually what they call the gross weight. The net weight would be the total weight. So what we do is we just set a zero reference. We just zero the scale out, right? And every scale that we had, and they didn't buy an auto zero circuit for this electric scale. So Rich designed one and built one. It was really cool. So, and it might still be out there, guys. I don't know. How much did I get for that? Nothing. No, it's part of the job. They did have a thing you could turn in once a year where you could submit modifications you made. I forgot what they called it, but I'd already got laid off before the years ran around. So these are some load cells, and these are some actually specifications. So this guy, the excitation voltage would be what? 10 volts. And then the output would be 300 microvolts per volt. So that means this guy right here, if it was rated, and they give us a weight, this one's rated at? Yeah, what's the weight it's rated at? When we bought them, they were rated at a certain weight. So the maximum I would get out of this thing would be 3 times 10, right? 300 microamps times 10. So that would be 3 millivolts. These are the truck scales that we had. That's the big chunk of metal that goes down through the center that actually warps with the weight of the big trucks, which is pretty neat. Oh yeah, big. These guys were about like this, and they're about that tall. And these were truck scales. But what was amazing to me is this big chunk of metal would actually squat down when these big trucks pulled up there. We had to climb under there, and we had to get a big jack and jack up the whole scale because it would be sitting right on top of the scale. And just jack it up and pull them out. They wasn't. They had so much weight on them, you didn't have to worry about them moving. So they wasn't bolted down or anything. They were just up under the weigh bridge. The weigh bridge themselves were so heavy that they didn't move. You know, they have. You pull a truck up on a scale, it's got to be made of pretty good solid metal. Uh, and, and sometimes they had to pit. They had it pit, especially on scales that were converted over from lever scales over to regular scales. So they had to have all the levers under that thing. But most of your truck scales, they just pour a nice flat tape thing of concrete and just and put bolts on it to bolt the scale down. Yeah, that's a slab. Right? This is another type of load cell. And what would happen is your strain gauge is actually mounted up in here. And what you do is you'd make one side permanent, and then you'd make your load. You can actually see load on this side. And what would happen is when you put a load on it, this thing would warp. And it would cause the strain gauge to do what? To warp and change its resistance. So we had all types, different types. These smaller ones like this is probably what's operating on the scale in like grocery stores and stuff like that. So grocery stores use strain gauge. These guys are extremely accurate. You can buy and sell off strain gauge, off of load cells, but you have to keep them calibrated. So that's one of the things I would do. So I was able to calibrate it. So we had a truck. We carried 50,000 pounds of weight on that truck, and we had a little kind of like a crane inside of it that we could come over and pick it up and drop them down and stack them up. You know, on truck scales, we'd put the 50,000 pounds on the one end, and we'd put them on the center, then we'd put them on the other end. And then you calibrate what we call the span. You calibrate the span on the scale. Because what would happen, and y'all might run into this, is that first of all, you would set a 0, right? Okay. Oh, it was up there. I just said it. So if you ever have to run into scales, what would you do is you'd come up here and you'd set a 0, and then you'd put weight on it, and then we would come over here and it would start off with a slant like this. Then you'd put weight on it and you'd adjust it. Well, as soon as you adjust this, what did you just change? You changed your 0. Well, that's what you had to do. You had to set 0, then you had to come up there and you had to put weight on there, and then you'd set 50,000 pounds, and then you'd take it off and you'd go back there and redo your 0. And it took about 4 different times to get the span set right. So it was interesting, especially driving that truck. It had a 10-speed transmission in it. And you had a little thing on it you had to pull. You have 5 gears, and then you had to pull up a little thing to get the other 5 gears. So I learned how to drive a 10-speed transmission, which I'd never done before. Okay, guys, you'll take a 10-minute break. So this is the ones that we had on our truck scales. Most of our truck scales, we used the 50,000 pound scale. On our track scales, our railroad scales, we had 6 load cells, and I think they were 100,000 pounds. That might not be right because you can buy these up to 400,000 pounds. But see, they come all in shapes and sizes. All we're trying to do is come up with a chunk of metal that warps with weight, right? You understand that? And then we attach the load cells to them. Normally we go in pairs of 2s. One of them they call the active gauge, one of them they call the compensation gauge, right? You understand that? Makes sense? And we combine that with a Wheatstone bridge inside the actual load cell itself. And then, like I say, we have 4 wires coming in. Usually it's shielded, so it'll have a shield around it. You understand shielded cables now, right? You understand that? So what is that? That means we just put a metal braid around all the conductors, and we use that to help prevent electromagnetic interference from getting into these low voltage devices. The 2 scales that I used to work on, electric scale, they're still in business. So these are the actual indicators. Electric scale was a scale that they bought that they didn't put an auto receiver circuit on it. So what would happen is these big trucks would come in there with all that lime. They'd spill a little bit on the scales, and the weight would go up, right? You understand? Huh? What's that? No, but those are on the wire going. That's the wires that's coming out to the load cells. Those are actually taking this voltage that we're getting off the load cells and bringing it into these guys, which are the indicators. And would bring these into the back. On one where we had multiple load cells, we run it through a summing junction. We just sum them all together, and that way they would give us an average weight. That makes sense. Which is pretty neat. So yeah, the shield, but that's not a shield on the strain gauges. The strain gauges, that's the shield wire that's on the actual conductors themselves that's taking this millivolts. So these guys are going to give us millivolts out. So and we called it millivolts per volt, and that would be what you excited them on, what we call it excitation. But you see on just about all of them, it was 10 volts, right? Yeah, 10 millivolts per volt means if it's a 50,000 pound scale, then you'd get 3 millivolts if you put 50,000 pounds on that thing. So, very, very low voltages. So we'd bring it into the scale, and of course the scale would have a bunch of amplifiers in it, and have a way to set the span on it where we could set 0 and then what an actual weight was. We had to have calibrated weights, and we'd have to take the calibrated weights from Montgomery every year, and they would actually check the calibration, make sure they were still correct. And you had to be licensed to actually calibrate the scales. You had to actually have. And then cardinal scales. This is up in Joplin, Missouri. I went to the plant, which is pretty neat. Almost got snowed in up there. Oh, so this is another way we can do it. This is a real cheap way. What we do is we use a calibrated spring, which means a calibrated spring is one that's precisely made so it expands tracks at a certain distance with force. These are pretty accurate also. They're not over a big wide range, right? You understand? Here they're using a potentiometer. It would actually take what a linear potentiometer that actually would give us. So a lot of our sensors got this mechanical. We're going to the other sensor to come up with a sensor. Does that make sense? So here we're calibrated. Basically would do nothing. One just moves a dial, right? But I was going to bring this into take the weight and convert it to voltage. And we know we can do that because like a potentiometer, right? Understand? So what would the potentiometer do? Well, when the force comes in, it's going to cause the spring to compress in this situation. It's going to compress pretty precise to what force you put on there. So the more force you put on there, the more it compresses. The less force you put on there, the less it would compress, right? Understand? And then we connect it to the watt. They got it connected to watt in here. A potentiometer, which would give us a watt, it would give us a voltage that indicates a weight. Now, right over force. Okay. So weight is usually vertical, force can be in any direction. You understand the difference? So this is just another example of what this thing would do. Everybody okay? So we got 6 volts exciting, right? You understand that? And we got 1 inch of motion. So what would be my transfer function from 0 to 6 volts? We got 1 inch. So what would be my transfer function? So we're getting volts out. We're putting. That's not right. Yeah, that would be 1 volt per inch. Plus 1 inch. What you mean? Yeah, I don't know what it's talking about right here. Because we're putting 6 volts on this side. Not unless it could only go half distance. Per 60 pounds per inch. Right. And that's what they're saying right here. That's what they're meaning right here. So we start off with 0, and then if we move 60 pounds per inch, right, so it's giving us our transfer function. Then it moved half an inch, then it gives 3 volts over here out of the pot, right? Would be 30 would be 30 pounds of weight. So 30 pounds of force. This is not weight. This is force. If it was mounted like this, it would be weight. If it's mounted like any other direction, it would be what force you're getting applied to it. Right? You understand that? Yes, no. There goes. This I have. This is not very accurate. I made one. Anybody got their own meter? No. There's a thing. Oh, that's not. I'm gonna pass this around. Y'all can look at it. Yeah, I can show y'all it. Then I'll pass you around and let y'all look at it. So I made one of these. So what we got is we got carbon. Carbon is a semiconductor, but it's really unique because how much resistance it has depends on how much you compress it. So the more you compress the carbon, the less resistance it would have. The less you compress, you compress, the more resistance it would have. That makes sense? So this was originally what they used, by the way, to automatically open doors on grocery stores. Some old grocery stores still have this. Yeah, but they have 2 rails on the side to make sure you step on the mat. And when you step on the mat, you would step on one of them. We still use them a lot in robots, where we put these mats down on the floor in front of the robots, and if a person comes in and steps on it, it's into the mat. We use it on a lot of iPads. The problem with the ones on your cell phones, these are what we call capacitive sensors. Well, the problem is if I put the buttons on, what happens? It can't work anymore. So most iPads we have out in the industry, the human machine interface, these displays, they work on this principle right here. So you come up here and you press on them, although you actually have to press on them, and it's what you're doing. You're generating watt in the center where the resistance is. Oh, those are capacitors. I don't know. Then it's going to have to be resistant. You can buy gloves that actually works with phones. Yeah, you got it. What's that? You have to push on that. That's actually a push button. Yeah, it'd have to be resistive, right? I understand what you mean. You don't have a real button? Yeah, Alex, I don't know how much you gave for his phone. I don't want to know, Alex. Oops, I didn't hook up my got my camera hooked up. So this is basically what we got. This is carbon impregnated. Uh, this is carbon impregnated foam. We use this. It's got carbon in it. We we use this, by the way, for electronic devices that are sensitive to electrostatic discharge, like the memory in your computer and stuff like that. What I've done is I've sandwiched it between two metal plates and put this on ohms. Try to get it in the display at the same time. And this is the bottom plate. Can you still see it? And this is the top plate. And it's give me that. And all I'm going to do is just come over here and press on it. Try to anyway. I just pass this around and let you do it. So you see the resistance goes down. I do what? Press on it. These guys are not very accurate, but like pads, like we said on robotics, it don't have to be accurate. Right? You understand? All it's trying to do is sense a big change in resistance, and all of a sudden it will trip over the robot if you walked into the work cell. By the way, we're trying to get a grant to get us what we call a collaborative robot. You know what a collaborative robot is? You work with all these sensors that automatically senses where you're. So hopefully we'll get that before next summer. Yeah, they all got one. We're looking at one. Those are very expensive though. I forgot who we're trying to get ours from. Somebody still has the somebody still has the program. So in motor controls, what do we use for symbol for a sensor? Yeah, it's a diamond shape. No dotted lines. Then we come over here and they draw a symbol for a limit switch. Yeah. And then if it's a 3-wire sensor, we would do this, right? If it's a 4-wire sensor, we would do that, right? But it don't identify what is this a photoelectric sensor? Is it an inductive sensor? Is it a capacitive sensor? Is it ARUC? Now I've seen them add some stuff like coming up here and they'll do this, and you'll know if they do that, that means it's some type of light sensor. Huh? We didn't have any sensors at all. The only sensor that you actually used was a mechanical sensor called a limit switch. And that's an electromechanical sensor, right? That was the only sensor that you actually used. So the symbol in motor controls, we don't really know. So what they've done since we moved into PLCs, what does PLC stand for? Anybody know? Controller. Well, in relays, we call it relay logic, right? That's when we started. And what was the logic that you learned in motor control? Yeah, you learned and, right? Or, not. Then we learned what? Exclusive or, exclusive nor. And like I said, we need to add labs on those. I don't think there's any labs in motor control. Well, what's happened since we moved to PLCs, so anywhere you go to, the main device now is going to be a programmable logic controller. And what it's going to do is it's going to replace every one of these guys. All these control relays. And why do we define a control relay? What is a control relay? So basically, control circuits are made up of two sections. We have a control section, and then over here somewhere we have a power section. And this is really prevalent. This is really now because of this National Fire Protection Association standard. Y'all know we have the National Electrical Code. This is actually the NASA 70 standard. What is the national? What does that do? What is the National Electrical Code? What does that deal with? But it's the safe installation of electrical equipment. Is there anything there that protects you? No. Now, normally, if you follow the National Electrical Code, you install it safely, it's going to be safe for you, but there's really nothing in there that actually comes up with what an employer has to do to make you safe. So what the National Fire Protection Association came out with, they came out with this 70E standard. And that's why this is safety. And OSHA, you don't make standards. OSHA usually adopts standards made by other people. Okay. So OSHA has adopted the 70E standard. NEC, the National Electrical Code, is not adopted by OSHA. And protected employees, right? Which means what? Well, the National Electrical Code is only a recommendation. And the authority that has jurisdiction, so here, Jefferson County Electrical Inspector for Jefferson County, they are the ones that decide to adopt the code. Once they adopt the code, it becomes law for the region. It don't mean it's going to be law for Shelby County, right? You understand that? So every authority, every jurisdiction in that area, they're the ones that set standards on how to safely install equipment. Now, just about everybody adopts the what? The code, because so one thing that 70E has established is what voltage is considered lethal. And what voltage is that? 50 volts. So anything below 50 volts is considered to be not lethal. Does that mean it won't kill you? No, it just means it's not considered. Anything above 50 volts is considered to be lethal, and that's where all So if I can keep that below, what it means is that my people don't have to, they still have to basically wear, you have to wear, right, ear protection. So a lot of places require you to wear hard hats. Right? But what advantage does high voltage have? What advantage does high voltage have over low voltage? What am I trying to deliver? Am I trying to deliver current, or am I trying to deliver voltage, or am I trying to deliver power? Power is work. So that means if I'm trying to deliver power and I'm trying to get it through all these different devices that have resistance, voltage is equal to I times R. Every wire has resistance. So I mean, if you push current through a wire, that is going to drop a voltage. And what determines the resistance of a wire? The material, the length, right? And the what? And temperature. They tolerance temperature. So if I'm trying to make my I lower and I'm trying to give power, power is equal to V times I. So that means I, the amount of I would be equal to P over V. So am I trying to sell you power? Which one delivers the lowest current, high voltage or low voltage? High voltage. So the higher I can make that voltage, the less current to produce power, which means my system is going to be a lot cheaper to install. I don't have to use these wires, right? And deliver my motors don't have to be as big. Those big gauge wires, power because we're running a lot. So this is why control circuits are made up of the low voltage side. We call it the control side. Without have a power capture that I provide lights on it that I can only get into. I have right to understand that. Most controls we have a low voltage control system. We have a high voltage power system. And all I do is I send low voltage over to big relays over my power station. So I can have a big relay that runs off 26 volts, right? And it can control all stuff, right? So a control relay is a relay whose contact so there we go over the power. This is what a PLC will do. It will replace every control. We don't actually have relays. We like to so PLCs are operating where? Over here. And we usually use 24 volts DC. 24 volts DC now. Well, I mean, 26 volts. The PLC, the electronics in the PLC operate off of DC. So I mean, if I use AC out here, I have to convert it to DC for the PLC. So why not just start off with what? DC, not 24 volts DC. Right? And I don't have to have an extra power supply that goes from an extra power supply inside my PLC. So what they've done and how does this run out to? What they've done is they've established symbols for sensors that make sense. Or the actual symbol identifies what type of sensor it is. And so you're going to have to learn this because what's the name of the class? Sensors. So I'll print this off and give it to you next class. No. Somehow I closed out my PowerPoint. Dang it, Rich. Here we go. I'm recording. I didn't close out my PowerPoint. So this is what we do. We put it in a square. And then we have a diamond shape that has two lines to it, indicating that it is a sensor. And then we put a little symbol to the lower left that identifies what type of symbol it is. So this little trough right here, let's see the little trough, that identifies it as some type of magnetic sensor. This is a reed switch. This is a Hall effect. So PLC has inputs. So this is the actual inputs of PLC, right? This is the power block. So what I'm doing is I'm running plus to every sensor. Notice that what power would that be? Ground. Then I'm running, this guy's going to negative. What? And notice the odds are power, the evens are outputs. And three, these are our power connectors, right? And for me, that's black. What happens to two? Well, it's a 3-wire sensor. So why they decided to use 4 will be if it comes out of 4, this is going to be black. This is going to be a only open output. White would come out would be number 2. It would be the Can y'all see the little trough in there? Right here. Yeah. So if I see that little thing over to the left, which basically looks like this, let me get a color. Usually this, we know it's some type of what? Yeah, some type of magnetic sensor. If it lets me draw. I'm trying, guys. That's good enough. Some type of magnetic sensor. If it's a 3-wire sensor, it's either a Hall effect or a magnetoresistant, which basically means nothing to us. It requires 3 wires, right? If it's a 2-wire sensor, then it's a Hall. It's a reed switch. Because reed switches don't have to be powered. Yeah, but they're both what? Magnetic sensors. So let me bring up this. And like I said, I'll run this off and give it to y'all next class, if I remember. So here we go. Let me see. Okay. So this little black pin thing right here, like this is a what type of sensor? Inductive. Everybody okay with that? Yeah. All these sensors will be on the next test. All these symbols will be on the next test. This, notice it's got it's like a capacitor, but it's got this little block in the center. This is a symbol for a what? Ultrasonic, which we've already talked about. This guy is showing a combination of an LED and a phototransistor. This is a what? Photoelectric. We already know this. This is not a Hall effect, by the way. That's wrong. How do I know it's not a Hall effect? Yeah. Oh, it's capacitive. I'm sorry. I saw this right here. This is a watt capacitive. No, this is not a Hall effect. I would have this wrong. Why is that not? How do I know that's labeled wrong? Well, we don't see the magnet. All we know is it's a magnetic sensor. It's going to be mounted outside or something. How do I know that's not a Hall effect? How do I know it's labeled wrong? It's got 3 wires. It's got one, right? It's got 1, 3, and 4. Hall effect. I mean, a reed switch. Uh, this is a Hall effect. Rich, you're getting crazy. This is a Hall effect. What would a reed switch have? 2. Thank you. I'm just making sure I'm paying attention. Here we go. This is a reed switch. This is right. 1 and 3. Remember these reed switches, the blue wire goes toward L2. So this one, the load would be connected to 3. On a 3-wire sensor, the load is going to be connected to either 4 or 2, right? You understand? We don't have any 4-wire sensors. So this means what? If we see this, it means it's what? Inductive. We see this, it means it's capacitive. We see this, they usually have arrows pointing out. This usually means what? Optical, right, or photoelectric. This means what? Magnetic. This is ultrasonic. And by the way, the international standard symbol for an open contact is this weird guy right here. But it makes sense. This is the international symbol for a normally closed contact. Yeah, it does. Yeah, they don't. And this is not our symbol. This is what you will run into now if you get out here on just about any plant that we got here. Now, when we come in and we actually look at the diagrams for these different sensors, and I'll try to find the symbol for a pressure sensor, which is not one that's on here. So when we start getting into these PLC diagrams, so this is normally open push button. This is normally open. This is an E-stop. Notice it's got the D10 on it, and it's got the little Z below it. Let's get to the next one. This is the sensor. So what type of sensor is this? Hall effect. This would be a what? Hall effect. This would be a reed switch. This would be a photoelectric. And but this is a standard drawing for a PLC connection. So so this would actually be the PLC down here. And we have what we call input ports. And this would be where the power is wired, right, on the terminal strip. What's that? No, on these, the way we do on these, and then after this, guys, we're going to let y'all split. That's what I meant. Yeah, I mean, it could be, but that's not. The PLC, we actually have This is actually a terminal board. No, that's this right here. This is the actual what you were looking at. This is actually a terminal board that's up on a circuit board that's on top of the actual unit itself. So what we can do with this guy is we can take a cable and then we can plug it into this connector right here, and then it automatically makes connection throughout the system. Does that make sense? So what we literally do, if you get back over to the manufacturing line, and we're supposed to at the end of the term, when we have one lab, we also go over there and find all these different sensors where they're at inside there. So you can actually see where it's got a cable on top. That way we can place the PLC real fast. We have the cables pre-wired on these. The problem with this PLC is that there's no way in the world that the terminal strip off most of your new PLC. The actual terminal strip on top of the PLC. You don't have to run it into a connector on the module itself. What's that? Yeah, but it's not removable. You can see it from the top, right? If you look in there. But most of your newer PLCs, the actual where you hook up to the I/O on the PLC, they'll actually snap off. There's two screws on the outside. You can unscrew them and snap them off, and that way you don't have to do any rewiring to actually replace the PLC. You just pop the terminal strips off, put the new PLC in there, download the programs into it, and just put them up. That's what most of the new ones work. To make it real fast to change them out. Because these guys do go bad. I mean, they're just like computers and your cell phone. You know, they're really rugged. And most of our watches and stuff we have now are pretty rugged, but we still do you know, like my grandkids, we've lost two where they left them on the car and they drove off. And one of them somebody ran over it. So they're not designed to handle that. So even these PLCs, if you put them down, that's the screen. Okay, guys. So we get more people in here next class. So that's basically all the force sensors that we're going to talk about. So we talked about there is another one I look at before we go lab class. But I can do power. I can't access my file server. That's why I'm going over there. Okay. I guess I could have showed y'all the little Siemens filters.